Good morning.
Good morning, my dear.
Good morning.
Good morning, dear.
Good morning.
Good morning, madam. Okay, girls. Oops, okay. So far, any questions? Okay. So let's see. So we mean, yes, okay, yesterday talked about period frequency. Right, okay. And okay, what we said was that period is inversely proportional to frequency. Another thing that we also said was that period multiplied by frequency equals to 1. Clear? Okay. Now, if you say that this is 1 second, to begin with, and we got, we can say it's okay. Two cycles in 1 second. Okay. Now, in this case, yes, okay, our frequency is going to be two cycles. Clear? And the period is going to be half a second. Okay. And they happen to be as okay reciprocal, because if you multiply half by 2, what do you get? You got 1. Did that make sense?
Yeah.
Good. Now we can say that if this period here was 1 millisecond, like from here to here. That period was 1 millisecond. Clear? So what do we have then? We can then mainly say that, okay, yes, the period of each cycle is going to be half a millisecond. That will mainly mean that, okay, yes, we will have a frequency of 2,000 cycles per second. Did that make sense?
For me, no. Can you explain that again?
If this period now here was 1 millisecond, what does 1 millisecond mean?
1,000.
Huh?
1,000? You said milli, so that's 1,000.
Is 1,000th of a second.
Yes.
Clear? So if in 1,000 or in 1,000th of a second, or in 1 millisecond, you have 2 cycles, your period is going to be as, okay, half of a millisecond, right?
Okay.
Right, okay. So in that case, it's okay, what will your frequency be then? You will have a total of 2,000 cycles per second, right?
Oh, okay. Now I get what you're saying. Thank you.
So your frequency could be either, if it says, okay, 2,000 cycles per second, or you can say it's okay, 2. The 1,000 here becomes just, okay, kilo. And we can say it's okay, the cycle per second is going to be as, okay, the hertz. So your frequency is 2 kilohertz because the period is half of a millisecond. Clear? Okay. And even yes, okay, when you multiply this half here with 2, what do you get? You get 2. Okay, but here, yes, okay, what is it that you see? That's the unit milli and the unit kilo were reciprocals to one another, right? One is a 1 over 1,000, this is 1,000. We can take the same example and say, yes, okay, if this period here now represented, we can say it's okay, 1 microsecond. Yeah. Then you mainly could say it's okay that the period for each cycle is going to be as okay half of a microsecond. Yeah. Whereas now your frequency is going to be 2 megahertz. Or you can actually say it's okay, you will have 2 million cycles per second. Right, okay.
So will it always be like reciprocal?
Yeah.
Okay.
That's why we said that period and frequency are reciprocal to one another. So if the frequency is okay, increase, let's say 10 times. Right, okay. The period is going to reduce to 1/10. Did that make sense?
Yes,
Okay, because what I mean, yes, I just did here, I said, well, okay, yes, this was the period in which we had 2 cycles. I mean, yes, okay, just kept decreasing that. What was going to happen? The period for each cycle was going to, yes, okay, decrease. But the frequency was going to equally increase. Okay. I reduced this period from here to here from, let's say, it's okay, 1 second. That's what I started off with. And I say, well, okay, that was the case. The period for each cycle was half a second. I said, well, okay, if this period from here to here, in which we had 2 cycles, is 1 millisecond, then the period for each cycle is going to be as, okay, half a millisecond. Clear? Okay. So here is okay, the period actually is okay, it's in this instance here is going to be as okay, 1,000 of what we want here. But the frequency is going to as okay, then increase 1,000 times. Because the period for each cycle decreased to 1,000, the frequency is going to increase 1,000 times. So you don't really need to just, okay, do much math. It is straightforward, girls. You can mainly say, that's okay. You can do it like this and say, it's okay, period and frequency. Okay, if the period is 1 second, your frequency is going to be 1 hertz. What I mean, that in a period of 1 second, you may just, okay, just had 1 cycle. The time from here to here was 1 second, and that's the time that it took 1 cycle to complete. So in 1 second, you will have a frequency of 1 cycle. Clear? If you, for instance, say that this is 1 second, and for instance, okay, let's just say that, okay, as we have a total of 10 cycles, then your frequency is going to be as okay, 10 hertz. But the period of each cycle is going to, as okay, be 1/10 of a second. Because in a period of 1 second, you have a total of 10 cycles. There's somebody there. Did that make sense?
No.
So what do you mean if I say that, okay, that they are reciprocal? Because you mean is, okay, just multiply the period by the frequency. What does that come out to? Sorry. It comes out to 1. If you say that, okay, you can do it in whatever way. You can say it's okay if this is 1 second. And if first that's okay, how? Because it's okay, 1,000 cycles. Now here's okay, that frequency is going to be, it's okay, 1,000 hertz. But the period, just remember what a period was, the time that it takes 1 cycle to complete. That is going to be, it's okay, 1,000th of a second. So what happens when you multiply 1,000 or 1/1000 by 1,000? What do you get? You get a 1. Clear? Now we can also say express this period here for each cycle can be as okay 1 millisecond, where you mean you can say here that okay as this frequency is going to be, okay, 1 kilohertz. Did that make sense? Or if you said that this was 1 millisecond, and in 1 millisecond we had just 1 cycle. You can maybe say, okay, in that case, the period for 1 cycle is 1 millisecond. That will mainly mean that, okay, as 1,000 milliseconds makes up a second, right? So in 1,000 milliseconds, you have 1 second in which 100 cycles or 1,000 cycles will be completed. So you still have, okay, as a frequency of 1 kilohertz or 1,000 hertz. Did you guys get that? We can go to the actual, yes, okay, ultrasound and say, yes, okay, if this is 1 microsecond, for instance. This is a period of 1 microsecond. And this 1 microsecond, what do we have? We can say, okay, we have 1 cycle. We have another cycle. And we have another cycle. So in 1 microsecond, we have a total of 3 cycles. That will mainly mean that, okay, yes, the period for each of these cycles here is going to be, okay, a 1/3 of a microsecond. Right, okay. Which means it will be that, okay, yes, if that's the case, in 1 second, we will actually, that's okay, how many cycles? We will actually, that's okay, end up with 1 million cycles per second. No, sorry, not 1 minute, sorry. 3 million cycles per second. Right, okay. Where you still can say, well, okay, yes, 1/3 multiplied by 3 is 1. You can mainly say it's okay, because here is okay, this is microsecond. And here is okay, that is mega hertz. Right, okay. So if you have a frequency of 3 megahertz, that mainly will mean that, okay, yes, the period of each cycle is 1/3 of a microsecond. If we had a total of, let's say, yes, okay, 4 cycles here. Okay, let's just, okay, extend this a little bit. And okay, I just made a 4 cycle. You can say, okay, so I just disregard this here. Okay, then we can say, it's okay, we have a total of 4 cycles per microsecond. Now, in that case, that's okay. Now the period is going to be 1/4 of a microsecond, which means you may guess, okay, your frequency be 4 megahertz. Because frequency and period are reciprocal. So when you multiply this by this, mainly because, okay, saying that a microsecond as a unit of time is reciprocal to, yes, okay, megahertz, or mainly because micro and megas are reciprocal. So that's why I said in chapter number 1 that remember that, okay, these units here are reciprocal to one another. That's reciprocal to deca. Right, okay. Centi reciprocal to hecto. Kilo reciprocal to milli. Mega reciprocal to micro. And giga reciprocal to nano. But the actual ones that you need to, okay, worry about is, okay, as kilos versus milli, gigas versus micro. Did this make any sense? Yes, girls. Or is this just sliding on top of your heads? Yes, girls. Or we can even, okay, maybe this will make some sense. Period. Frequency. If period was 1 second, frequency was 1 hertz. Period was 1/10 of a second. Now this 1/10 of a second that could also be written as 1 multiplied by 10 raised to the power minus 1 second. Then you can mainly see as, okay, that the frequency would have been 10 hertz. This 10 hertz here can also be written as 1 multiplied by 10 raised to the power 1 hertz. You say 1/10 of a second is 1 decisecond. Clear? We can then go and say as okay, if the period is 1/1000 of a second. Now here's okay, there's 1/1000 of a second. Makes it a millisecond. Now that can also be written as 1 multiplied by 10 raised to the power minus 3 of a second. Now 1 is 1. 10 raised to the power minus 3 becomes the milli. And second is second. That will mainly mean that, okay, as in 1 second, we actually, as okay, will have 1000 hertz. Where we can say as okay, this 1 is 1. This 1000 here can be as okay, 10 raised to the power 3 hertz. Or it can also be written as 1 kilo. Or where you look here, 10 raised to the power 3 multiplied by 1/10 raised to the power 3. Where this here actually is okay, is the same as saying 10 raised to the power minus 3. Of the unit being expressed. Clear? If we go and say yes, okay, that the period is 1/1,000,000th of a second. Now, when we say period, what would that be? The time that it takes one cycle to complete. Okay. Then we will actually say, okay, have how many cycles per second? The reciprocal of this number, which is going to be 1,000,000. Okay, 1 is still 1. This million here is going to be, okay, be the reciprocal of this, which is 1,000,000th. Or we can say, okay, 1 micro, or micro is reciprocal to mega. That's all.
I have a question.
Huh.
Can we put hertz on the millionth side or like the decimal side, or do we always have to put it on the frequency? Like on the
Hertz
period,
is going. How many?
like on the period side, can we put
Yeah.
hertz on that side? No,
No.
it's always
Because-
going to be on
No,
frequency.
no. Why? What's the unit for period?
Start with a P. I forgot how you say it.
Now, what's the unit for period? Just answer my question, dear, and you will answer your own question.
Seconds, right?
Seconds. Or any unit of time. Any
it.
unit of time is going to be the unit for period. So when you say second, minute, hour, days, years, centuries, millennium. Clear? Okay. Now what we defined as period here was what's the time that it takes one cycle to complete. Clear? Now if one cycle takes a second to complete, then on the other hand, you will say, okay, what is going to be your frequency? Now you just look at the definition of frequency and we say, okay, yes, number of a specific event completed in a unit of time. Now in this case, yes, okay, we took that unit of time as a second. The specific event completed is going to be as okay cycles. So how many cycles are completed in a second is going to be the frequency.
Got it.
And the unit for frequency is hertz. You can go multiples and say it's okay, decahertz, hectohertz, kilohertz, megahertz, gigahertz, terahertz, whatsoever. Clear? Okay. But the more you increase the frequency, that will mainly mean that, okay, as more and more and more and more cycles will be completed in 1 second. Which means to me that, okay, then the period of each cycle will become shorter and shorter and shorter. How frequently do we have presidential elections?
Every 4 years.
Every 4 years, right? Okay. Okay. Now, if they say, well, 4 years, that's too short a time for a president to become a sitting. We should elect a president who at least has, okay, 10 years. Now, as it is now, what is the frequency of, let's say, it's okay, presidential elections in a period of 20 years? 5 times, right? If we increase the period for a sitting president to be elected for a period of 10 years at a time, then how many times would you go for a presidential, or it's okay, voting in a period of 20 years? Only twice, because you increase the period. Did that make sense? If we say, okay, let's just say, roughly speaking, the duration for us, okay, your physics module is 3 months. 3 months, right? Okay. That's the period for your physics module. Now, if I say that you will have a test every week, now you can mainly say, okay, the time period from test to test, from test to test, to test to test is going to be 1 week. That will mainly mean that you have an average of, let's say, it's okay, 12 tests in the module. So your frequency of tests is going to be as, okay, 12 tests per 3 months. Whereas if I say, no, you're only going to have, yes, okay, 1 test per month. So between test to test to test to test, now I increase the period from 1 week to 1 month. Now what's going to happen then? The frequency of your test is going to become 1/3, right? Or 1/4. Did that make sense? Now I give you a test. Let us look at this. Let us look at it in this form. Okay. And okay, as I say, well, okay, girls, you have 10 minutes to answer this test here. Let's see, let's say that, okay, as I time your test, I gotta do that. Right, okay. Now, in that test, that's okay, there was a total of, let's say it's okay, 10 questions. What would that mean? That you have, yes, okay, 1 minute to answer each question. Because I say, well, okay, as this test here is going to be due to, yes, okay, submitted in 10 minutes and there are 10 questions. So the period that you have to answer each question is going to be 1 minute. Whichever way, let's say it's okay, I still only give you 10 minutes. But then it's okay, I now increase the number of questions to, let's say, 100. And say, okay, here's a test with 100 questions, you have 10 minutes to answer that. What does that mean? Then now you have to answer, yes, okay, 10 questions per minute. Which now doesn't give you, yes, okay, 60 seconds or 1 minute to answer each question. You have 6 seconds to answer a question. So you can see, yes, okay. Okay. As the frequency of questions you have to answer per minute increases, the time that you have for each question is going to decrease. And we can say that's okay reciprocally. Because 10 questions, 10 minutes, minute per question. 10 minutes, 100 questions, 10 questions per minute. So you can actually say it's okay, you have 6 seconds per question. If I go even more bananas, I give you, it's okay, 1,000 questions. And self says, okay, 10 minutes. Now you have to answer 100 questions in a minute. That's going to be 0.6 of a second. Not even a whole second. So period and frequency are always going to be, as okay, reciprocal. If that makes sense. But when you look at the typical values of, okay, as ultrasound, or let's say as, okay, the frequency of ultrasound, we say, okay, that was 2 to 15 megasecond or megahertz, right? Right? Which mainly means, okay, that the period was 0.06 microseconds to 0.5 microseconds. Any questions? Now goes the reason that we call them ultrasound, or the reason that we call it ultrasound, is mainly as okay, all as okay due to, you can say as okay, the audibility of the human ear. And we can say it's okay, oh no, not that okay, yes, we can say it's okay, practically relevant to ultrasound. But as actually as okay, something that we call as okay, infrasound. And infrasound, that is mainly as okay, going to be as okay, we can say, now we can actually look at it in this way and say infra is below. Sound here is mainly as okay, just sound. It can also as okay be replaced by the word sonic. But as okay, here we can say, okay, this sound or sonic is going to be as okay, human audible frequency. So a sound which is infrasonic is mainly as okay because it has a frequency which is below the human's ear ability to listen to it. So that's going to be as okay. Any frequency that's going to be as okay less than 20 hertz. So you can say it's okay, a frequency or a sound which has a frequency of, let's say, it's okay, 18 hertz. It is still going to be a sound, but the human ear is not going to be able to detect it. So that makes it okay an infrasonic.
Professor?
Yeah.
I'm sorry, how do you spell that? I'm just having a little bit of a hard time reading it, the word.
This
Intrasonic, you said?
infra, it's infra.
Oh, infra. Okay, thank you.
Infra below, right? Supra above. Clear? So it's INFRA. Is that better?
Yes, thank you.
Okay. Clear? So any sound with a frequency less than 20 hertz is going to be infrasonic. Or we can say, okay, be an infrasound. Mainly because, okay, it's going to be a frequency that is going to, okay, be below the human ear's audibility. So a sound of 20 hertz, just okay, you will not be able to hear it. Now, what does it mean to be 20 hertz? That's okay, yes, if we had, okay, let's say it's okay, a period of 1 second, that the actually is okay, was just going to be as okay, a total of 20 cycles. That makes it as okay, 20 hertz. Okay. So we can mainly say, okay, the sound that is going to, as we can say, the audible range of the human ear is going to be as okay, between 20 hertz to 20 kilohertz. So as long as a sound has a frequency that ranges between 20 hertz, which we could say is okay, mainly was going to be as okay, 20 cycles per second. And 20 thousand hertz. Which also is okay, could have meant it's okay, the same 20 thousand. And this will mean it's okay, this be cycles per second. That's the audible range of the human ear. Okay, so it's okay in 20 cycles per second to 20,000 cycles per second. So if we had, let's say it's okay, 1 second here. This here is okay, was a period of 1 second. And we had a total of, let's say it's okay, 16,000 cycles per second. That was going to give us a frequency of, okay, 16,000 hertz, which was going to be, okay, audible to the human ear because it falls within these two ranges here. Clear? Okay. Now this 20 or 16 hertz here, or 16,000 hertz, which means that we had, okay, 16,000 cycles per second. In that case, that's okay. You can say it's okay. The period was going to be, it's okay, 1 over 16,000 of a second. Or we can also say it's okay, this could be, it's okay, 1 over 16. Sorry, milliseconds. Why? Because here it's okay. It is 16. And this is just kilo. Did that make sense? So this 16 kilohertz could also be written as 16 multiplied by 10 raised to the power 3 hertz. Or you can also write it as 1.6 multiplied by 10 raised to the power 4 hertz. This 10 raised to the power 4 actually is equal to as 10,000. Because when you multiply 10,000 by 1.6, you still get 16,000. Okay. So as long as a sound frequency ranges between these two ranges here, that is going to be audible to the human ear. Anything less than is okay, these 20 hertz is going to be infrasonic. And then we just go to okay, let me just erase all this here. Because the next is mainly what we just can call as ultrasound or ultrasonic. It's going to be okay. First of all, it is going to be okay. But we can do it this way and say it's okay. The ultra here is going to be okay. About human ears audible frequency, which mainly means that it's going to be any frequency which is greater than 20,000 kilohertz. An ultrasound is mainly going to be greater than 20,000 hertz. Or we can say it's 20 kilo hertz. Or we can say 20 multiplied by kilo, which is going to be, it's okay, 10 raised to the power 3 hertz. Okay, bye. Right, okay. Or we can even say it's okay, anything that's going to be greater than 2 multiplied raised to the power 4 hertz. So when we look at, okay, as the typical value of your ultrasound frequency for diagnostic imaging, that's going to be, okay, far more than 20,000 hertz. Because we actually, as okay, are talking at a minimum of, okay, as 200,000 hertz. Yeah, this actually is, okay, was going to be 200,000, sorry. Okay, which was going to be 2 is 2. This and this becomes a mega and becomes a. So it's actually, it's okay, 100 times, 100,000 times greater than the maximum audibility of the human ear. Not to talk about, it's okay, where if we say it's okay, 15 megahertz. Which is okay as the maximum higher range of your ultrasound frequency. Okay. But as far as, okay, as audibility of the human ear is concerned, anything greater than 20,000 hertz or 20,000 or 20 kilohertz, sorry, the normal human ear is not going to be able to hear. It is too loud for the human ear to be able to detect it. Did that make sense? So when we go far on the as okay ultrasonic scale, in 100,000s times the upper limit of the human ear, that's where it's okay, the lower limit of your ultrasound transducer starts. Did that make sense? Okay, let me see. Okay, girls. Let's see, like that. Let's see. Okay. Girl is just Don't look at your books right now, look here. And our main is okay, give you goals, 2 things to remember. This is very, 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 very important, 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 important. And we can mainly say, okay, the frequency of the sound wave is related to the penetration of the sound wave. And what do you mean by penetration? Because that's okay, the depth to which it travels. That is going to be, it's okay, related to the frequency. And we can mainly, as okay, say it this way here is that the frequency and penetration are inversely related, which mainly mean that, okay, yes, the greater the frequency of a sound wave. Let's say it's okay that we take the max 15 megahertz. That sound wave will have, okay, as a lower penetration. Whereas if we take the other way and say, well, okay, yes, a transducer with a lower frequency, let's say it's okay. Well, let's just take the minimum. Here. And say it's okay. 2 megahertz. That transducer will have a greater penetration. Okay. Is that clear? So you can say maybe it's okay, a high frequency transducer may as okay, we can just say, may just penetrate, yes, okay, we can say it's okay, at depth of 2 centimeters. Now this is not an authentic number, but just okay, give you girls a comparison. Okay. So it has okay as a low penetration. It mainly is okay, just penetrate 2 centimeters deep into the body. Where if it has okay a 2 megahertz transducer, it's going to have okay a greater penetration. That actually it's okay that the sound wave actually can penetrate at a depth of, that says okay 15 centimeters. But just remember, guys, that's okay. The greater the frequency of a transducer, the lesser will be the penetration. And pretty much, okay, what they mean is, okay, if I said, okay, well, this is our upper limit, mainly because what they mean is that I found, okay, is if we increase the frequency about 15 megahertz, that would mainly mean that, okay, as there will be no penetration of the sound wave. That the sound wave actually is, okay, are going to die off even before it's, okay, they enter the human body. And in that case, that's okay, what is it that you have? Well, okay, yes, if we don't send any sound wave into the human body, we are not going to get any reflections back, which is going to just, okay, produce our image. Is that clear? So good is good, but then too much good is bad. Okay, so we can't say, well, okay, we can have an unlimited high frequency of the transducer. No, it has an upper limit because they say, well, okay, here, beyond that, it's not going to do its job. Did that make sense? Okay. But the difference between, yes, okay, low frequency transducers versus high frequency transducer is going to be how much is it that the sound will penetrate into the body. And the more it's going to be able to penetrate directly, it's okay, be able to, it's okay, because it's okay, send sound waves to a greater distance and okay, send reflections back. And it's going to be, it's okay, based on those reflections that we will have, or it's okay, the images are going to be produced. Okay, let me see. Now, just another point. And what they mainly say is higher frequency transducers are better for diagnostic imaging. Now, just keep in mind that, okay, as this, we can say it's okay, higher frequency transducer that comes with an upper limit. Clear? Okay, but what we mainly as okay can say is that okay, as the higher the frequency of the transducer, the better it's going to be as okay, we can say it's okay, the diagnostic image. Because as I guess going to give us okay, what we later on as okay, we refer to as a better resolution of the diagnostic image. Okay. So higher frequency transducers, yes, okay, gives us better resolution of diagnostic imaging. Where, okay, as we can say, lower frequency transducers, mainly as okay, will give us okay, yes, a poor resolution for diagnostic imaging. Okay. Now, girls, what I would like you ladies to do is reread on your period and frequency. And then you have, yes, okay, a total of 10 questions, page 25 and 26. Okay. Now you will have to go over those questions. Okay. And okay, yes, when we come back, if you still have any doubts, you can ask. And if not, well, okay, yes, we can still look at the questions together and try to, yes, okay, reach an agreement. And after which, yes, okay, we will jump on to page 33, which is going to be wavelength. Okay. So I see you ladies at, should we say 10? 10:45. So reread your frequency, read your period, and do those questions at the on page 25 and 26, which are regarding period and frequency. Apish? Okay, girls, welcome back. Now, are you guys clear about frequency versus period? Now, just mind my word, this is going to be okay, a kind of relationship that's going to come back again and again and again and again. Okay. Now, did any of you have the chance to read through the topics?
Yes.
Okay. Yeah, that's I don't doubt that you didn't, but okay. Good. Did you guys try to answer the questions? You were given 10 questions of period and frequency to answer, right? Now let's see how much you got out of all this. What is the period of the Earth rotation around the sun or around the sun? If this is the sun, how much does it take the Earth to rotate from here all around the sun and come back? That's going to be, it's okay, 1 year, 365 days. Is that clear?
Yeah.
Good. We can take next question. So you can mainly say it's okay that every 365 days, the frequency of trip of the Earth around the sun is 1 for 365 days. Right, okay. Now question number 2. A top is spinning on a table. What is the period of the spinning top? Now, this is maybe it's okay, just a question I ask you, it's okay. Do you know the unit for period? Because it's okay, we say 4 pounds. 4 pounds, yes, okay, that's a unit of mass. Or it could be pound sterling, which is okay as the currency of England. But anyways, it says okay, $8. That means okay, going to be a unit of currency. It says okay, 0.05 seconds. Okay, I mean it's okay because this here is a unit of time. That becomes just okay, the period of the spinning of the top spinning on top of the table. Clear? Whereas centimeter, well, okay, that's a unit of length or distance. Did that make sense?
Yeah.
Good. So it's just a matter of, okay, as do you know the unit for period? What period? It is the time. And event takes to complete. Or our ultrasound, that event was 1 cycle. So the time that it takes from here to here, oh, this is 1 cycle, that's going to be the period. I mean, it's okay because it says the time is going to be using a unit of time. Second, minute, hour, days, millisecond, microseconds, whatsoever. Question number 3. Now, which of the following waves are infrasonic? Now, what did we mean by being infrasonic? You mean it says, okay, waves frequency that was less than 20 hertz. So the main ask is, okay, which of the following waves of frequencies given here is less than 20 hertz? Okay. Now don't fall for the number because, okay, what we mainly see here is, okay, there's a number that says 4. Because 4 is, okay, that's a number that is less than 20. But then you look at the unit, which is megahertz, which actually is, okay, means this many hertz. Clear? Did that make sense? So that is not less than 20 hertz. As a matter of fact, it's greater than 20 hertz. Clear? Although it's okay, we still have okay as a number here, which is okay, as we can see, 400. And on top of that is okay, we go with okay as kilohertz. But this kilo here actually is okay means another 1,000. So 400,000 kilohertz. Or we can actually say it's okay, 0.4 megahertz. Clear? Then is another one. 28 hertz. Now that is still greater than 20 hertz. Clear? Okay. Where, okay, the next one is just 2 hertz. Now, main is okay, just means 2 cycles per second. Well, mainly here, it says, okay, 2 is less than 20. So that's just okay, as frequency of 2 hertz is going to be as okay, infrasonic frequency. Okay. Now, just out of the blue, always okay. That's not what I asked in the book. But if this was your frequency here, 4 megahertz, my question is, what's going to be the period? If you had a frequency of 4 megahertz, what is going to be the period?
One over 4.
Pamela? Yes, Thomas, what did you say?
1 over 4,000. 1 over 4 thing.
Okay, 104. What horses, donkeys, apples? One over 4 what?
Second.
Seconds. Okay. And then you will be asking me, say, why is my answer wrong? Because it is wrong. Microseconds. Dat dwars dat sakay. Okay. If this is your frequency then, 4 kilohertz, then what's going to be the period then? if your frequency is 4 kilohertz, what is going to be the period? Not for 400 kilohertz, sorry. What is the period then? Yes, girls.
I don't know if it's right, but is it one over 4 milli?
Just give me what you think it is, and you're going to get whether it's wrong or right.
Okay, so
I say you have a frequency of 4,000 hertz. No, not 4,000, sorry. 400 kilohertz. What's going to be the period then? What is your period for a frequency of 40,000 kilohertz? Or 400 kilohertz, sorry. What is the period if your frequency is 400,000 kilohertz? I'm not reading chats. Speak the answer out.
can it be 1 times 10 to the power of -3? Seconds?
No,
Okay,
because you only took the kilo here. What about these 2 zeros here?
oh,
It would have been 10 raised to the power -5. Or you can say it's okay. It's going to be this.
Sir, would the period be on? Okay.
Is it 1/4?
1/4. And then with 5 zeros. Half a second.
Sir, could you say it was 0.0025? Would that be a wrong answer too?
Pardon me now?
Never mind. It's okay.
You go by ones, which you go by zeros, okay, 2.5,
Yeah, that's what I was asking.
0.5. Then you also have to consider all these zeros here. So that's going to be as okay, 0, 0, 0 point.
It's 0.0025.
Something like
Okay.
मजा नहीं आया. Now I may still ask, if this is your frequency, 28 hertz, what's going to be the period then? Yes, girls, what's going to be the period if your frequency is 28 hertz?
1/28 hertz.
Okay, 1/28 hertz. That's what you said, right?
Yeah.
Good. And my dear, your question is still wrong. You know why? So what is the unit for period? Is that hertz?
Seconds.
It would have been seconds, not hertz. Question number 3. No, 4, sorry. Now identify the wave that is ultrasonic. Okay. Now the first one is 400 MHz. Now just keep in mind, girl, this here is a lowercase m, so that's going to be as okay, milli, which made as okay will mean 1000. Okay. And that's not going to be the case, because that will mainly mean that, okay, yes, that in 1 second, right, okay, you would actually have, okay, yes, .4 of a cycle in 1 second. So a cycle is actually going to take more than 1 second to complete. Clear? And that cannot be as okay an ultrasonic. Okay, it would have been okay as another case had this as okay had it been an uppercase, because then it would have been a mega. Okay, it would still have been as okay beyond the human or frequency, which was beyond the audibility of the human ear. Clear? Did that make sense? So that's okay. Look out for the upper and lower cases. Now we can say, okay, the next option that we have. Reads 4 megahertz. Now 4 is 4. Mega here is 10 raised to the power 6 or a million. And hertz is hertz, which means it's okay, just is translated as okay as cycles per second. So 4 megahertz, it becomes 4 million hertz, or 4 million cycles per second. Clear? And that was beyond, and this number here is actually is okay greater than 20,000 hertz. or we also said, okay, it's 20 kilohertz, which made it an ultrasonic sound. Did that make sense? Whereas, okay, the next one is 28 hertz. Right, okay. Which was not ultrasonic, it was not infrasonic, it was within the, sorry, audible range, which was 20 hertz to 20,000 or 20 kilohertz. And then the same, 2 hertz. Now this one here was, okay, yes, infrasonic. So let me see. What's the period for this frequency here? Four megahertz or 4 million hertz. What's going to be the period if your frequency is 4 megahertz?
Wouldn't it be 1/4 million seconds?
You can say, okay, 1/4 million seconds. Who was that?
It was me.
Okay, good job. And this 1/4 million of a second can also be written as 4 multiplied by 10 raised to the power minus 6 seconds. Where this means, okay, becomes okay, 40,000 or 4 million. And mainly because the exponent here is negative, it becomes a fraction of 4 raised to the power 10 raised to the power 4 multiplied by 10 raised to the power 6. Now, question number 5. Now, which of these waves is ultrasonic and is useful in diagnostic sonography? Okay. Now, if you look at it, 400 megahertz. Now we can with surety say that, okay, this is, of course, greater than 20 kilohertz. Right, okay. So why is the next one? It's also greater than, okay, yes, 20 kilohertz. Now 2 kilohertz. Okay, that is lesser than 20 kilohertz. So since that cannot become, yes, okay, an ultrasonic sound, because it is lesser than the upper range of, okay, as the human audibility. So is right, we can say it's okay. Now if we say that's okay, 200. Yes. Okay. Which means it's going to be as okay, we can say it's okay. 2 megahertz. Because 2 is 2. This is this. This is another 10.3, which becomes 10 raised to the power 6. So this is there, yes, okay, greater than 20,000 hertz, or what we could say is okay, 20 kilohertz. But then comes the next thing, okay, and most useful for diagnostic ultrasound. Now this one here is okay, that was far beyond the upper range. This one here is okay, that was just at the bottom. So that's why they go with this one here, 4 megahertz. This one here cannot be used, that's too high. Because it says, okay, the upper range was 15 megahertz. Did that make sense? Did that make sense, girls? Identify all the waves that are inaudible. Now, what does it mean to be inaudible? Because, okay, its frequency was less than 20 hertz. Or if the frequency was greater than 20 kilohertz. That makes it inaudible. Okay, and here they even gave you the answer. It's okay, say, okay, it's more than one answer may be correct, but just look at it. 4 megahertz. That's greater than 20,000 or 20,000 kilohertz. So that is inaudible. So can we say it's okay? Or 400 kilohertz. It is still greater than 20 kilohertz. So that may still is going to be okay, inaudible. Clear? Now, when we look at 28 hertz, that falls in between this range here. It is greater than 20 hertz, but it's less than 20,000 hertz. So it falls in between, yes, okay, the range of these two here. So that is going to be as okay an audible frequency. And then we go as okay and say 2 hertz is less than 20 hertz. So that again, yes, okay, becomes an inaudible frequency. So the one here, the only one that was audible here was 28. The inaudible ones were 2 hertz because it was infrasonic, 4 megahertz because it was greater than 20 hertz or 20 kilohertz, sorry, and 400 kilohertz. Clear? Where this 400 kilohertz goes also as okay, going to be as okay 0.4 megahertz. They're both the same. This could be written as 4 multiplied by 10 raised to the power 5 hertz. Where we say as okay, 2 of the 5 here comes from here. And we can say as okay, 3 of the 5 hertz here come from this. So this could also has been written as simply 4 like this, and then it's okay, just simply it's okay, your hertz. So you can say it's okay, 400,000 hertz. Clear? Whereas if you want to, as okay, as written the same in this, okay, using megahertz, it would have just become 0.4 multiplied by 10 raised to the power 6. Because 0.4 is 0.4. 10 raised to the power 6 becomes your mega. And then the hertz is the hertz. Is that clear?
Yeah.
Good. Question number 7. Now, which of the following waves has the longest period? Now, the main is okay, just asking us okay for the longest period. Okay. And what they have done here is okay, they have given off okay as they have given up different frequencies. Now, first of all, as okay, you say as okay, you should know as okay the relationship between period and frequency. that they are inversely proportional. Not just inversely proportional, they are also reciprocal. So if they're asking you for, yes, okay, the greatest period, they may indirectly asking you to, yes, okay, pick up the lowest frequency. Did that make sense? Yeah. No, we can mainly, yes, okay, just look at the different frequencies that we have. We have, okay, yes, 2 megahertz. Where, okay, as we know that mega is a multiple of frequency, which is going to, yes, okay, make it, okay, it's a big number. But anyways, let's see what we have next. 4,000 hertz. So we can say, okay, here we have 2 million hertz, here we have 4,000 hertz. That is still high, but not as high as 2 megahertz. Then we have, okay, 6 hertz. Now 6 is, okay, as a low number, and okay, as it's not a multiple. So we can say, okay, we are looking at a low frequency. And we say it's okay, 1 kilohertz. Yeah, 1 is 1, but this actually is okay, becomes 1,000. So it's okay. It's still a high frequency. So this here has the greatest period because it is the lowest number of cycles per second. They had asked the opposite way and say, it's okay, which of the following has the greatest, or sorry, the least period or shortest period? And now being had just been asking which of these is the greatest frequency. And that would have been this one here. Yeah, because this is actually, it's okay, 2 million hertz. This here would just have been, it's okay, simply 4,000 hertz, or we can say it's okay, 4 kilohertz. And this one here is okay, it's mean it's okay, just 1 kilohertz, or we can say 1,000 hertz. So this will be the lowest period because they're going to be, it's okay, half of a microsecond. For this one here, it's okay, your period would have been 1/1000 of a 1/4 of a millisecond. Here your period means it's okay, just 1/6 of a second. And here it's okay, your period is just 1,000 of a second or 1 millisecond. Yeah. Question number 8. Now, R are the 4 waves whose periods are listed below. So yes, okay, we have 4 periods. okay, which has the fourth highest frequency. So here's, okay, what are they asking us? The highest frequency. Or that's okay, the 4 periods that we have been given. But mainly that's okay, now you should know by the relationship that, okay, they're indirectly, that's okay, just asking you which is the shortest period. Clear? So we have, okay, yes, different periods. We have 8 seconds. We have 80 microseconds. Well, actually, that's okay with me. $80 over a millionth of a second. Then they have, okay, something that they say is okay, is 80 megaseconds, which actually is okay with me. $8 million seconds. Clear. And then they have, okay, as 800 kiloseconds, which is going to be as, okay, 800,000 seconds. So the shortest period here is, okay, as 80 microseconds.
So, sir, question, when there's a question like that, so whenever they ask the highest frequency, you just have to remember that they're asking for the shortest period?
Yes.
Okay.
Why? Because of the relationship between period and frequency. If you don't know the relationship, you are going to be LOST. Now, if they just had asked the opposite, and say, okay, of the 4 periods given below, yes, okay, or listed below, which has the highest frequency? Okay, that's what they asked. I had asked which has the lowest frequency. Now, lowest frequency may know me as, okay, which is going to be as, okay, the highest period. And then that would have been, okay, as 8 megaseconds. Because 8 megaseconds is going to be, as, okay, 8 million seconds. That's going to be several days now, maybe even months. Okay, but just because, okay, you're asked, yes, okay, find the lowest period. As okay, find as, okay, the period with the lowest, highest frequency. In the book doesn't mean that, okay, that's going to be the way that you'll be asked in the test. They can flip everything around. And that's why we said, first of all, that's okay, that frequency is inversely proportional to period. But then on top of that, we also said, okay, frequency multiplied by period equals to 1. This just makes them, yes, okay, inversely proportional. This here is, okay, staged, okay, that they are reciprocal.
I have a quick question.
Mhm.
So on question 8, it says for D, it says 800 KS. That's per
Yeah.
kilo second. Is
Yeah.
that like basically trying to trick us so we know, like, instead of them putting hertz, they put seconds?
Permitted?
Is
I didn't get
they
your last part.
is the KS for kiloseconds? Is that same as saying kilohertz?
No.
No.
Why would that be the same?
Because
It can never be the same. It's rather reciprocal.
the
When
S
you
that,
say, when you say kiloseconds, second is second, right?
yes,
What does kilo mean?
1,000.
1,000. So XYZ kiloseconds is going to be XYZ 1,000 seconds. When you say, and that's why I even wrote it here. I don't know what the hell you guys are doing. 800 kiloseconds. I even wrote it out in numbers. Where you can say, it's okay, this is your 800. This is your 800, right?
Yeah.
Gets this becomes this. And so it becomes just, okay, 800,000 seconds. That's 8 kiloseconds, or 800 kiloseconds, sorry.
I think I tricked myself up because when I see K, I just automatically, or like a mega or kilo, I always think it's what hertz, and the
No,
fraction part
no,
of it
no,
is
no.
what
But
seconds. It's
because,
not that.
okay. Hertz, my dear, is the unit for frequency.
And this is asking, and we're. and
This second, what is second?
Period.
Second is the unit for period. So you can't express frequency in terms of seconds. You can't express period in terms of hertz.
Got it.
It's not saying it's okay if I give you 5 donuts and you say, okay, that's $5. No, I gave you 5 donuts. So you count them as 5 donuts, right?
Yes.
Yeah, what is going to be? It's okay. Well, okay, it's probably not going to be possible, but we can say it's okay if this was okay as your period. This is your period, right? Okay, 8,000 or 800,000 seconds or 800 kiloseconds. If that is your period, that would mean that, okay, as your frequency, that is going to be as okay 1 over 800,000 of a hertz. Which mainly mean that, okay, as in 1 second, only 1 over 800,000 of a cycle is going to be completed. Because it's going to, yes, okay, take your cycle 800,000 seconds to complete. But you can't say that second is going to be the unit of frequency. That is as wrong as it can be. Likewise, hertz is never going to be as okay the unit for period. What this hertz here means as okay is going to mean is cycles per second. So whatever number is going to be written here is going to mean as okay be how many cycles do we complete in a second. Do you get that?
Yes, I did.
Good. Question number 9. Of the 4 waves whose frequencies are listed below. So now they have given us, okay, as a list of frequencies. Okay, which has the shortest period. So they mean, yes, okay, when they ask us about, yes, okay, the shortest period, it's indirectly, yes, okay, just asking us to pick up the greatest frequency of the list that we have been given. Clear? Now, the first one says A reads 12 kilohertz, which mainly means 12,000 hertz. B reads 6,000 hertz, which also had been 6. And these 1,000 here is okay, could just be a kilo. And then the hertz would have been hertz. C as in cat. 205 hertz. No kilos, no megas, no dekas, no nothing. So 205 hertz. Now, if you want to, you can say, okay, if this is going to just okay be expressed as, let's say, kilohertz, it's going to be as okay 0.25 kilohertz. Clear? Just so you see, well, so you have. So here, okay, you actually have a fraction of a kilohertz, right? Okay. And then we go, yes, okay, D is just 1 simple kilohertz. Now, mainly because, okay, they ask us, okay, which of these here has the highest frequency? You're just going to just, okay, pick the greatest number, which is 12,000 hertz or 12 kilohertz is the highest frequency. Which then we just, okay, just have the lowest period. Whereas had they asked us the other way around and said, okay, which of these frequencies here has the greatest period? That would mean just meant that they had asked you just, okay, pick up the lowest frequency. And here's, okay, our lowest frequency is this one here. Because it's a fraction of kilohertz. All the others were just, okay, multiples, or just, okay, simply just 1 kilohertz. Obviously, it's okay, 1 kilohertz is 1,000 hertz. 6 kilohertz or 6,000 hertz is 6,000 or 6 kilohertz. 12 kilohertz is 12,000 hertz. Whereas this was mean as, okay, just 205 hertz. Which is mean as, okay, 0.205 kilohertz. So that is mean as, okay, going to be as, okay, the lowest frequency. And since as the lowest frequency is going to, as, okay, be the greatest, is okay, the sound wave that has the greatest period or each cycle. Because here, or this one here is okay, your period or mean is okay, is just going to be 1/12 of a millisecond. Or this one here, 1/6 of a millisecond. Okay, here, 1/1000 of a second, or you can say it's okay, which will be same as saying 1 millisecond. Did that make sense? Now, question number 10. Of the 4 waves whose periods are listed below, which has the lowest frequency? So yes, okay, what have they done? They have given us, okay, yes, or it's okay, 4 different periods. And they mainly, it's okay, just asking us about, it's okay, the lowest frequency, which mainly mean that they are asking us to pick up the greatest period. Now, answer 1 here is 8 seconds. The next one here is 80 microseconds. But you can say it's okay, 80 is still 80. But then the microsecond actually is okay, makes it a fraction of a millionth of a second. Clear. So although yes, okay, 80 is greater than 8, but mainly because okay, this is a smaller unit, yes, okay, this already is okay, is a low period. Then okay, option A. Then have C, which is okay as 8, which is the same number as we have here, but I will say as okay, megaseconds, which actually will mean 8 million seconds. Clear, and not just okay, 8 kiloseconds. And I think we just had these numbers as okay, in question 8. Okay, where this 800 kiloseconds actually means 800 becomes 800 kilos, just going to be as okay. Another 1,000 and then seconds. Your main, yes, okay, just not to look at, okay, yes. Which 8 here, yes, okay, has the greatest number of zeros behind it or following it. That's going to make it, okay, as the greatest period. And that's this one here. So that's going to be as okay, the sound wave, or that's going to be the wave that has the lowest frequency, because it's going to be, well, probably not going to be possible, but anyway, you can say it's okay, 1 over 8 millionth of hertz, because it takes one cycle 8 million seconds to complete. Whereas if they went the opposite and say, it's okay, which is going to as okay be the highest frequencies, maybe as okay going to be the one with the lowest period, and that's going to be this one here, because it is 80 microseconds. Here, as a matter of fact, yes, okay, if this was our frequency of, or because there's okay, if our period was okay, that's 80 microseconds. Okay. The frequency actually becomes 1 over 80. I'm sorry. It actually becomes, because that's okay, 80 megahertz. Okay, why did I write 80? Meaning because 80 comes from here. Where, okay, yes, micro and mega are reciprocals. And just yes, okay, because second is the unit for frequency. This is the unit, oh, sorry, so second is the unit for period. Hertz is the unit for frequency. So 8 microseconds, 800 microseconds is going to be as okay, 8 megahertz. Any questions? Okay, girls. Now you can take your lunch, and when you come back, I can only wish you best of luck for it. Okay, starting with the wavelength. Okay, so I see you girls no later than, okay, yes, 12:45. Okay, ladies, welcome back. Now, any questions, girls? Any questions, girls? Okay. So, yeah, okay, so far we have minutes, okay, just said. This. We can also say the period that's going to be as okay. The time for one cycle to complete. Clear? Where frequency was just going to be the number of cycles, or time. Clear? If we can say here, if we just have one cycle, then we have okay as a frequency of 1 hertz. 2 cycles, for instance, then it was going to be as okay 2 hertz. Clear? And the more we increase the frequency, the lower and lower is it that the period is going to be. That makes them reciprocal. Now goes for now, just skip the 3 bigness parameters. We're going to talk about those hopefully tomorrow. So I will ask all of you, it's okay to jump onto page number 33. And we will actually, it's okay, start off at what we'll call wavelength. And if you just look at the word wavelength, now we can say wave, that is going to be, it's okay, the same of cycle. And when we say length, that means it's okay, just means that's okay how long it's going to be in terms of distance. Yeah, so that's means it's okay going to be what the length of wavelength is going to be. So that is going to be the distance, or we can say length of one cycle. Which we mainly can say is okay, it will be like this. That this is one cycle. So if you actually, it's okay, measure from here to here, like this, that is going to be, it's okay, the wavelength. Okay, girls, your wavelength, and please mind it, your wavelength is not going to be this measurement here or this measurement here. Okay, that is not your wavelength. But pretty much, okay, we can say, okay, from the beginning of a length of a wave to the end of the wave, when we measure that in terms of distance, that will become the wavelength. Or we can just mean, yes, okay, say as we did for period, that, okay, yes, that's going to be as, okay, the distance, or as we say, length. Right, okay, which means, yes, okay, it's okay, is from, let's see, from beginning of cycle to the end of the cycle. Now, please keep in mind, those are okay, as the word cycle can also, as okay, be replaced by wave. It doesn't really matter. It's the same. So the distance from, yes, okay, the beginning of a cycle or wave to the end of a cycle of wave, that distance is going to be the wavelength. Did you girls get that? Clear? Okay. Whereas if you measure this here in terms of time, then that will become period. Clear? So you should already, as okay, be able to, as okay, figure out something and say, okay, that means, yes, okay, make wavelength directly proportional to period. Clear? Now goes the unit. The unit that we're going to, yes, okay, measure the wavelength in. Mainly because, yes, okay, it's all talking about, yes, okay, the distance, the length of the wave from the beginning of the wave to the end of the wave. Clear? So mainly it's okay because it's talking about, it's okay, how long is it that the wave is in terms of distance? It's mainly it's okay going to be using a unit of distance or length, which can be centimeter, it can be millimeter, it can be micrometer. Okay, it doesn't really matter. It can even, yes, okay, be meter. Now in ultrasound, we're probably not going to have, yes, okay, sound waves which are going to, yes, okay, be meters long. Okay, they usually, yes, okay, one that we may see is okay as centimeters. Oh, sorry, millimeters. But if I just say it's okay, if some wave had okay as was said okay as 1 millimeter. Right, okay. We can put it this way. And it says, okay, if a wave had a wavelength of 1 millimeter, let's just assume that this distance here was 1 millimeter. It isn't, but let's just assume. and we express that using the unit micrometer, then that is going to, yes, okay, be 1,000 micrometers. Or if we say, okay, yes, the wavelength was 1 millimeter, then how much is it going to be? As okay, if we express it in terms of centimeters. Anybody? Yes, girls. One millimeter is equal to how many centimeters? Okay,
1,000?
that's huh?
That 1,000?
1,000. Okay.
Can it be 100?
Okay, somebody goes with 100 centimeters. Okay.
0.1,
Huh?
0.1
0.1 what?
centimeters.
Exactly. Now, those who got 1,000 centimeters is 1 millimeter. 100 centimeters is 1 millimeter. I don't know what to say. Thousand would have been the right answer. No, funny. Okay, yes. And I said micrometers, which was right here. Hundred centimeters, my dear. That is 1 meter. Okay. So that's okay. When we talk wavelengths of sound waves, that's okay. Ultrasound waves, let's put it this way. We most likely is okay, we use the unit of millimeters, or is okay, micrometers. Clear? But if you say it's okay, 1 millimeter, that is going to be as okay, 1,000 micrometers. Because micrometer is a smaller unit than a millimeter is a bigger unit. So that's why, okay, as here, yes, okay, the number is lower, and here the number is greater. So your wavelength, girls, is always going to be used, it's going to be expressed using is okay, a unit of distance, because the main is the distance from the beginning of the wave or cycle to the end of the wave or cycle. Now goes here, it's okay, for once, that's okay, there's a typical value that you don't have to remember. Okay, but what they mean is that's okay, just say is okay, that the typical value. Or yes, okay, because it says okay, ultrasound, sound waves, wavelength is equal to, I mean, that's okay, is going to range from 0.1 millimeter, which means that okay, will be as okay, be the lowest, to is okay, 0.8 millimeters, which is going to be as okay, the greatest. This 0.1 millimeter here actually is okay, is going to be 1/10 of a millimeter. Which is the same as 1/100th of a centimeter. Or actually it's going to be, it's okay, 100 micrometers. Whereas the maximum wavelength is 0.8 millimeters, which is meaning that's okay, 1/8 or 1/10 of a centimeter. Oh, sorry, this is 1/8 or 1/10 of a millimeter, which becomes 1/8 or 100th a centimeter, and so on. Okay, but really now it's okay, a typical value that you have to remember. Okay, so it's okay, it's mainly it's okay, just mentioned here, but it's not something that you may remember. Now, if you look in the text, it mainly says, okay, in clinical imaging, wavelength in soft tissue ranges from 0.1 to 8 millimeters. Clear? Okay. So soft tissues. Now that's something that, okay, as we will talk more about, is okay, when we get to, as okay, propagation speed. Well, it's okay, the soft tissue here and its relationship to, as okay, wavelength is going to be, as okay, a hot topic. Now goals, when we go to, as okay, be determined by, or we can mean it's okay, wavelength of the sound wave. Now this is going to be, as okay, the only one of the 7 parameters that is going to be determined by both source. And here's okay, when we say source, that's okay, what we actually mean is the transducer. And medium. Clear? Right. Where our average medium is going to be as okay, what we can call as okay, soft tissue. What goes out of your 7 parameters, which are period, frequency, wavelength, amplitude, power and intensity, and propagation speed. Wavelength is the only one of them which is determined by both the source, which would be as okay, the transducer and our system. But here's going to be the transducer and medium, which mainly as okay is going to be as okay our tissues. Okay, but as okay, where you as okay more likely as okay when we talk of tissues. A mean average tissue that you will hear us talk a lot about is going to be as okay what we will call soft tissue. As a matter of fact, that's okay. Most of it is okay. Whenever we say tissue here in the book, in 99.9% of the cases, okay, we will be referring to as okay, soft tissue. Okay, girls. So for now, just remember this much, that this is the only of the 7 parameters which is determined primarily by both the factors, which was source and the medium. When we said period, that was determined only and only by the source. It was the transducer that determined the period of the sound wave that it will produce. So like for frequency, it was the frequency, it was going to be as okay, the source, or you can say as okay, the transducer that would determine the frequency of the transducer. Or let's say, okay, the sound that was being produced. But here, well, okay, yes, the transducer may produce as okay a wavelength which has its length. But that wavelength may change as it travels through different mediums. And okay, there is a little relationship here that we'll come to in just a little bit. Did that make sense? So for now, it's okay, just remember this one. Wavelength only want to be determined by both source and medium. Any questions? So from time to yes, okay, from time to time, as okay, or in your book, you may come across okay as what your book name as okay as hints. And they are highlighted not just for yes, okay, again, they're not highlighted just to give you yes, okay, your book a nice cosmetic look. They are highlighted for a reason, to attract your attention. So most of those hints, yes, okay, make sure that you, yes, okay, know them on the top of your tongue. Awake, asleep, in coma, whatever. So what was wavelength? It was the distance, or it was the length of a cycle. Is that clear? Now, why did I skip our bigness parameters and jumped all the way as okay to wavelength? Mainly because that's okay, there's one thing that we will look at now, and we can say it's okay that or we may as okay, we'll establish this fact here that okay, as wavelength, that is going to be as okay directly proportional to period. Clear? Which mainly will mean that okay, yes, if the period of a cycle is longer, that will mainly mean that that cycle or wave also will have okay as a greater wavelength. Yeah, but we can say it's okay here longer in terms of time. Then okay, here is going to be longer in terms of distance. Okay, but we said that they are directly proportional. That will mainly mean that okay, yes, if we have a wavelength with a shorter period, which again is okay, there's going to be as okay a shorter time duration. That will mainly also mean that okay, this wave here is going to have okay as a shorter wavelength. Did that make sense? Now we can make this okay, just do it this way and say, let's say that this here is okay is 1 second. And okay, just two is okay, not make it just okay, too complicated. We can say it's okay that this here also is going to be as okay 1 second. So maybe it's okay to establish this relationship. We say that if you, for instance, okay, had a wave with a great period, like this, and like this. Now, what did we have? We actually, it's okay, had two waves in 1 second. So here we come in, it says, okay, that the period will be as okay, half a second. Mainly because it's okay. If this here was a second, we come in and says, okay, that this was going to be as okay, a half second. This here is okay, was going to be another half second from here to here. But we can also say that, okay, yes, they will have this will be the wavelength. If it's okay, meaning measure this from here to here, that will be as okay, the wavelength of the first wave, and this will be as okay, the wavelength of the second wave. Now, if you mean that's okay, just do it here and say, well, okay, if we have waves with, let's say, it's okay, a shorter period. Here we had, okay, as half a second, we can make it as, okay, now we actually have, okay, as 4 speed cycles in a second. In this case, yes, okay, what do we have? Our period actually becomes 1/4 of a second. Here, where you can mainly say as okay, because from here to here, that's 1/4 of a second. This will be 1/4 of a second. This will be 1/4 of a second. This will be 1/4 of a second. Clear? Where you can mainly also say as okay, now when we measure the distance then. And this way as okay will be as okay, the wavelength of the first cycle. This will be the wavelength of the second cycle. This here will be the wavelength of the third cycle, and this will be as okay, the wavelength of the fourth cycle. Where you can mainly say as okay, roughly speaking, that okay, as if you just label them here as, because A and B. That in A is okay, the period was twice what we had in B. And you also see as okay, that here, this distance here in A where we only had one wave, is going to be the wavelength of this one red wave here. Where, okay, as for the same distance in the example of B, we actually is okay, where we had a period or where we had a wave with a lesser period, we actually is okay, we're able to fit in two waves. Where we can make say this would be the wavelength of wave 1. This would be as okay, the wavelength of wave 2. Where we add these two up, and that's going to be as okay, equal to as okay, the first wave here. So mainly as okay, based on that, we can say as okay, the shorter the period of the wave, the shorter is going to be the wavelength. Clear? Okay. Or longer the period of the wave, the greater is going to be the wavelength. Which means it's okay, just establish the fact that wavelength and period are directly proportional. And when one increase or when one is great, is okay, then the wavelength is also going to be great. But okay, we have a shorter period. That mainly also means that okay, as we will have a lower wavelength, which was here. Here. Did you get that? Okay. So you can mainly say it's okay, measuring the wavelength and measuring the period is mainly as okay, measuring from same point to same point. But in one case, we measure in terms of time. In the other areas, okay, we measure in terms of physical length. So the greater the time, the greater the length. Clear? So that makes period and wavelength directly proportional. Simply straightforward, directly proportional to one another. Did that make sense? Now, have you guys heard of the function called copy and paste? No, Medina? No? Just give me a second, girls. Sorry, girls. So what are we going to do now? Copy and paste what we have been talking about for the last day and a half. And to begin with, mainly said the period was inversely proportional to frequency, right? Which mainly meant that, okay, yes, if we had a great period, we would have a lower frequency, right? Whereas we said, okay, yes, if we had a lower period, a shorter period, we will have a greater frequency. Did that make sense? Or does it mean that's okay, what we already is okay? We already know that. We have established this fact here. That period and frequency were inversely proportional. So that mainly also makes wavelength being inversely proportional to frequency. Which mainly will mean that, okay, as when we have a low wavelength, that's going to be as okay because we have that transducer here has a high frequency. Or if we have a greater wavelength, that's going to be because, okay, that transducer has a lower frequency. Okay. But here it is not going to be reciprocal. Okay, the reciprocal is okay relationship between frequency is okay, and any of these two parameters here only accounts for period. Okay. Or you can say mainly because okay, wavelength and period is okay, we're on the same page. When one increases, the other also increases. And period and frequency is okay, we're on opposite sides. That when one increased, the other decrease. When one decrease, the other increase. That is mainly going to be because it says, okay, since okay, these two here have a common relationship together. That may mainly mean that okay, as they both will share the same relationship with frequency. Okay, so whichever way you want to look at it. So yes, okay, you can be given a question and say, yes, okay, you have two transducers. Or they may give you a say, okay, as one transducer have, okay, as a wavelength, or let's say it's okay, 2 millimeter, and another transducer has a frequency, a wavelength of 4 millimeters. Now, the next thing they can ask you is, okay, which of these two transducer here is okay, may have, okay, as either, yes, okay, the highest frequency, or which of these two transducer here, okay, have the lowest frequency. So it's all a matter of, yes, okay, just knowing, yes, okay, where is the relationship between wavelength and frequency. So highest frequency, that's going to be, yes, okay, the lowest wavelength. Because wavelength and frequency were inversely proportional. And vice versa. So the greater the wavelength, the lower the frequency. Did you guys get that? Now just be watchful because they say is okay. If they give period and frequency, then it's also going to be inversely proportional. Whereas they say it's okay, period and wavelength, it will be directly proportional. And what does it mean to be directly proportional? If one increases, the other increase. If one decrease, then the other decrease. So longer period, greater wavelength. Shorter period, shorter wavelength. And vice versa. Okay. But then you say period and frequency were inversely proportional. Hence is period, and hence is wavelength and frequency also going to be inversely proportional. Because period and wavelength both are directly proportional. Did that make sense? Okay, girls. So on your page number 34, do everybody have their books on you? Because now, yes, okay, starts the nightmare of wavelength. This was just basics. Now, if you read the bottom paragraph, or yes, okay, there's something written in bold letter that says, and please mind each and every word here. Okay, girls? It reads in the bold letters. What is the wavelength of a 1 megahertz sound in soft tissue? Okay. Now, what did we say earlier? That sound waves wavelength is not only determined by medium, or not only determined by source, but also tissue. And why you guys will realize, okay, when we get to speed of sound or propagation speed, is that, okay, yes, there's going to be this, okay, a median or intermediate speed, which is going to be the speed of sound in soft tissue. Clear. A mean average tissue that we mean is, okay, just, now we, but it's okay, that actually is, okay, made for, yes, okay, you can say it's okay to understand ultrasound physics. Clear? But here is, okay, they set the frequency as, okay, as 1 megahertz. So the answer for that is going to be that we can say it's okay. In soft tissue, the wavelength, or let's put it this way, in soft tissue, 1 megahertz frequency transducer, or 1 megahertz. Let's sorry. And 1 megahertz okay, sound. Now, what does it mean to have 1 megahertz? That means it's okay going to be saying 1 million cycles per second. Or we can say it's okay, 1 million hertz. But in that case, that's okay. We can say that, okay, as the wavelength, that is going to be, is okay, equal to 1.54 millimeters. So what I would recommend that you girls do is mark that last paragraph on page 34. Now, some of you will go, yes, okay, Mike, where does this 1.54 come from? Why couldn't it just have been 1 millimeter? And that's mainly because, yes, okay, goes, we can say, yes, okay, knowing the frequency. And if we say, yes, okay, soft tissue. Sorry. we actually, it's okay, calculate. We can actually, it's okay, calculate the wavelength. So the formula is mainly going to be as okay, that wavelength. And please keep in mind here, it's okay, that this wavelength here is okay. Will be as okay measured in millimeters. Clear? Which mainly as okay is going to as okay be, there's 1.54 millimeters here. Divided by the frequency. In soft tissue. Now go this 1.54 millimeters here. Okay, that is actually okay derived from the speed of sound. In soft tissues. Maybe actually that's okay. We'll see that later on that that's going to just okay. 1.54 millimeters per microsecond. That's going to be as okay the speed at which sound is going to as okay travel in soft tissues. Or this 1.54 millimeters per microsecond, which is the speed of sound in soft tissue. We can also as okay express it as okay as 1,540 meters per second. But pretty much okay as from this one here. That's what they mean is okay, just copy and paste here. And you can then say as okay, now why do you use millimeters and not meters? Because okay, the frequency here is in megahertz. And if the frequency is in megahertz, that's because something is expressed in per microseconds. So if you go on GSOK page 35, the actually is okay. The next paragraph then just says, okay, what about a 2 megahertz transducer? A 2 megahertz is okay transducer, a sound wave, when that travels in soft tissues. Then what's the wavelength? And that's where it's okay, the formula comes. Okay, that okay is 1.54. And please keep in mind, that's okay derived from it's okay, the millimeter version of the speed. And that's why it's okay, your wavelength in this case is okay, is going to be as okay calculated in millimeters. But if you divide that by okay as this 2 megahertz frequency, then in that case, that's okay, the wavelength is going to be as okay 0.77 millimeters. You can even take it to the next level and say, as okay, what if it is a 3 megahertz frequency transducer? And they ask you, okay, then what is the wavelength then? It's the same. Is that 1.54 divided here is okay by the 3 megahertz. And in that case, that's okay, the wavelength is going to become 0.5 millimeters. And you can go on. But they're most likely not going to go as okay greater than that. You can say it's okay just if you go and say, well, okay, it's what if okay, it's okay. So this number here is okay, 1.54. That's fixed. That's not negotiable. But if you had, okay, it's a 15 megahertz frequency. Then you can actually say it's okay that the frequency or the wavelength is going to be, it's okay, 0.1 millimeter. Also, the wavelength is going to be, it's okay, 0.1 millimeter, sorry. Clear? So goes this formula here is okay, that is a must to know. The wavelength can be calculated as okay if you know the plane frequency. Just keep in mind, okay, as it will be megahertz. When we is okay, get the speed in millimeters or wavelength in millimeters. Because this number here, 1.54, is taken from the speed of sound in soft tissue. But you can mainly see it's okay as we as okay increase the wavelength. Also increase the frequency more and more and more. Okay. All right. 2 is a lower frequency, 3 is a higher frequency, 15 is an even higher frequency. But at a 2 megahertz frequency is okay, we had a wavelength of 0.077 millimeters. Where, okay, as when we increase the frequency from 2 megahertz to 3 megahertz, we end up with a shorter wavelength, which is 0.5 millimeter. Whereas if you okay, increase the frequency even more, we end up with a shorter wavelength, which is 0.1 millimeter. Actually, that's okay, the same as 1/10 of a millimeter, where this here was 0.5 millimeter. Did that make sense? So lower frequency, greater wavelength. Higher frequency, shorter wavelength, and very high frequency, very, very short wavelength. Which mainly is okay, makes frequency and wavelength inversely proportional. Or we can say mathematically, it's okay, that's how you calculate the wavelength in soft tissues, knowing the frequency. Clear? So that 1.54, that number is fixed. It's constant when we talk soft tissues. If they go and talk about other tissues, then the wavelength will change. Because what did we say? Wavelength is not only determined by the tissue or by the source, but it's also going to be determined by the medium. Clear? Now just back to, yes, okay, chapter number 2. And what did we say there? Sound may travel at different speeds in different mediums, right? You remember that one? That, okay, as if it's solid, it's going to be, as okay, a rapid speed. If it's slower, it's going to be as okay, or if it's a liquid, it's going to be as okay, a slower speed. And if it was gas, it was going to be the slower speed. Now you can also see as okay, we have tissues which are solid like bones. We have tissues which are liquid like, or medium which are liquid like blood, lymph, pleural fluid, pericardial fluid, urine. And then we have tissues or as okay, which are gases, or as okay, tissues which are going to hold gas. Your stomach, your lung, and all that. So sound is going to travel at different speeds in those different mediums. Is that clear? But there's a catch, and it's not directly mentioned in your book. And that's what I'm here for. To make sure that you girls get it. So write this down. And we can mainly say it's okay that it's going to be, it's okay, and we can say an increase in speed of sound. That is actually as okay going to lead to, we can say it's okay, an increase in the wavelength. But the same goes as okay with decrease. Clear? So if the sound is traveling through a medium at a greater speed, that is going to cause that, okay, as the wavelength in that medium or tissue is going to increase. Whereas, okay, if sound wave is traveling in a medium with a slower speed, that's going to cause that in that medium, yes, okay, the wavelength is going to be lower. Is that clear? Did you girls get that? Did you girls get that? But then there is a but, and it's a big but. That's what one T, okay? But it's going to be a big but. And that big but is going to be that, okay, as an increase or decrease in the wavelength. That will not lead to a increase or decrease in the speed. of sound in medium. So whether you have, let's say, it's okay, sorry, 2 megahertz. We can say it's okay, we have two different waves with two different wavelengths. We can say it's okay, 2 millimeters wavelength. And okay, yes. A 1 millimeter wavelength. When they travel through, that's okay, the same tissue. That's going to be, it's okay, the same speed. That is for B. Whereas for A, we can say it's okay, at great speed, we can say for instance, that's okay, 200 meters per second. And that's a low speed, so we can say, okay, that's going to be as okay, lead to a low wavelength. We can just say as okay, just for the hell's sake, 2 millimeters. Whereas, okay, I said we have a great speed. Let's say it's okay, 2000 meters per second. That is going to lead to, yes, okay, a great wavelength. So great speed and low speed is going to lead to respectively as okay, great wavelength and low wavelength. But great or low wave or small, shorter and longer wavelength is not going to cause a greater or short, it's okay, or lesser speed. So speed affects the wavelength, wavelength does not affect the speed. Okay. Yeah.
So the wavelength and the speed is inversely related proportion?
No.
So say that again.
Well, okay. It's not a matter. They are going to be directly proportional.
Okay.
Okay. But it's only going to be the speed that will affect the wavelength. The wavelength will not affect the speed. So if you have two different transducers with two different wavelengths, right? I say as okay, you have a 2 megahertz transducer versus let's say as okay, a 5 megahertz transducer. Oh, sorry. A wavelength that as like a transducer will produce a sound wave which had a 5 millimeter wavelength versus that's okay, 10 millimeter wavelength. When those waves travel through the tissue, they will have the same wavelength, irrespective of which transducer. So wavelength does not affect the speed. But the speed of sound in the medium is going to just okay affect the wavelength. So that's okay. The proportionality here is just one way. It's only going to be the speed that will affect the tissue at the wavelength, not the wavelength affecting the speed. because the speed is, after all, it's okay, going to be determined by the medium. But mainly because, okay, speed determines, or is determined by medium, and it affects the wavelength. That's how we say that wavelength is determined both by source and medium. The medium factor is because it's going to be affected it's going to be affected by the speed at which the sound travels through the medium. Clear? Or if yes, okay. Now that formula that we talked about earlier, where we said, okay, yes, where we said a wavelength, okay, yes, there was equal to 1.44 millimeters. And because it's okay, we divided that by, okay, as the frequency. Clear? Okay. So that will give us the wavelength. Now we can say it's okay. Now what? Okay, and this here is okay. This speed here is okay. That was me. It's okay, derived from the speed of sound in soft tissue. Now there may be, okay, there may be, it's okay, we can say it's okay, we talk about, and we keep the frequency the same. Okay, just for this case here. But when we say it's okay, we may talk about it's okay, another tissue may say it's okay, or we talk about something like bone, where the speed actually is okay, is going to be as okay greater. The speed of sound actually is okay will be traveling at a greater speed. It's approximately as okay, some because that's okay. That's okay. 5 millimeters per second, for instance. So mainly because okay, it is a different tissue with a greater speed that's going to cause that, although it's okay, the frequency here is the same. You can say it's okay, 2 megahertz and 2 megahertz. That the wavelength becomes greater because the speed at which sound travel through the tissue is greater than it was in soft tissue. Whereas if you go to, yes, okay, something like air, that's very actually is okay, it does have okay, it's a speed of, let's say it's okay, 0.5 millimeters per microsecond. But still, it's okay divided by it's okay, the same frequency. You're not playing around with the frequency. So here it's okay, your wavelength is actually it's okay going to be less because the speed of sound was in this medium here is okay, was even lesser. So that's how we mainly can say that okay, as sound affects or speed of sound in a medium is okay, is going to affect the wavelength that the sound have in that medium, but not vice versa. Okay, girls. So read through this, look at it, and tomorrow is okay, we will talk the bigness parameters. So you guys have to look at, okay, as your frequency and period. And now also is okay, your wavelength. What you mean is, okay, just can look here, it's okay, from the equation. And we say it's okay, wavelength also equal to, yes, okay, this, which was okay, derived from the speed. But then we say it's okay, frequency, yes, okay, where is that? There is a denominator of the equation. And that will mainly mean that, okay, yes, the greater this number gets, the wavelength gets lesser. Because you divide 1.54, which is constant, with a greater number. So that makes us, okay, wavelength and frequency inversely proportional. Just like, okay, as frequency is also as, okay, inversely proportional to period. So since period and frequency both are inversely proportional to frequency, period and wavelength, since period and wavelength are both inversely proportional to frequency, period and wavelength are both directly proportional. Okay, so at the bottom line goes, it's not really a lot on the math, it's more just, okay, the relationships that are important. But when I tell you to just, okay, mark an equation, you mark that equation. So yes, okay, this is going to be as, okay, an equation that you will have to know, yes, okay, on the tip of the heart, because it's going to be very easy to make, okay, calculate a wavelength. And it's going to be equally easy to just, okay, step in the soup, because you didn't know the equation. And when I told you to mark it, then I don't know why you wouldn't. Okay. See you ladies tomorrow.
Thank you.
Welcome, dear.
Thank you.
Thank
Okay.
you, bye.
Right, dear.
Good night.
Good night, dear.